All right, let's get started. So it's my pleasure to introduce today Victor Yakovenko from University of Maryland. So I actually know of, just as a sort of enthusiast, sort of reading some of these articles from the side of his work on applying ideas from statistical mechanics to problems in economics for a long time. But I think Victor has done a lot of sort of very nice work, kind of taking ideas and the sort of philosophy of a physicist and studying problems that normally would not be considered within the scope of the physics department. So I very much like that style of thinking. He's won a number of awards. He was a Packard and a Sloan Fellow, if I recall correctly. But yes, he wrote a very beautiful Reviews of Modern Physics on this subject. Is it okay? It's listed there. Yes, in 2009. And so it's my pleasure to have him come and tell all of us about it in person. So please welcome.
Okay, thank you very much, Andy. Just one sec, before you turn it off. Before I start, is my sound good now? Okay, before I start, I want to advertise my talk tomorrow. Tomorrow, Thursday, 2:30 p.m. at Engineering. This is at Applied Mathematics, a Dynamical Systems Seminar. This is on the subject of the mathematics of human population growth and CO2 emissions. This is my latest work I did about last year, okay? And I highly encourage you to come. It's very interesting. Not related to the economic, not related to this one, but in a similar vein of physicists doing something, which is not physics, okay? And this has expiration date because in this work we make predictions that something will happen by 2030, in 5 years. So if you don't listen it now, 5 years later it will be too late, okay? Okay, fine. So let's now start the main presentation. Okay, great. So basically, what I'm going to do today is I will present review of the work that I have been doing by about 25 years. So in the year 2000, I published my first paper on the subject, and the title is "Statistical Mechanics of Money." Okay, so that will be the first item on the list. And now this paper is my most cited paper. It exceeded whatever did in condensed matter physics, because basically by going into money, I branched to a much bigger market. Okay. So anyway, so this is some outline of the papers, Reviews of Modern Physics, bunch of other papers, and I'm still doing this. The latest paper, 2022. So basically, the outline is this. First part will be the main idea, how I started StatMech of money. I will probably skip that because time is short. I will show you then empirical data on income distribution, quite important. And finally, I really want to get to the last part. It's about global inequality, as measured by energy consumption and CO2 emissions. Okay, so anyway, I hope I will get to all three parts. Okay, so let's start. Just a second, what's going on? Okay, fine. Okay, no. Okay, I see what. Okay, fine. Hey, not a problem. So point is, because it's colloquium, I just want to show a little bit, very quick slide on historical. Ludwig Boltzmann, I'm sure you all know, one of the founders of statistical physics. And what is really associated with his name in statistical in physics textbook is this Boltzmann-Gibbs probability distribution. I'm sure you all know. The probability distribution of given certain energy is exponential decrease in the function of energy with a parameter called temperature. Okay. So this is Wilfredo Pareto, whom you probably may not know exactly, but he is also, by education, he graduated from Politecnica di Torino, so he's an engineer by education, you might say physicist, but then he became a very well-known economist and sociologist, and he lived at about the same time, even look a little bit similar. What economists and social people know very well, what is associated with his name, is power law distribution of income, money, wealth, whatever. So basically in those late 19th century, he looked at the data and published a paper saying that it follows a power law distribution, okay? Those two simplest mathematical functions, power law function associated with Pareto and exponential associated with Boltzmann, will show up repeatedly through the talk. We'll get later to them, okay? So now let me start, and basically let me start with this main idea of a certain analogy between distribution of energy in physics and money or later income. So how this whole thing gets started. Okay, so half a slide on foundations of statistical physics. Again, you all know. Let's consider like an ideal gas. So we have a bunch of atoms, they're colliding, and when, like billiard balls, and when they collide, some energy delta epsilon get transferred from one atom to another. So those initial energies, this energy after collision. Of course, energies are conserved, energy is conserved, so the total is the same. Now you have a big ensemble of those colliding atoms, and you ask, what will be the probability distribution of energy in statistical equilibrium, okay? And we all know the answer. So there are many ways to derive it. Well, one, for example, by detailed balance, but maybe I'll not actually. I will go, to save time, I'll go straight. So bottom line, we know that in statistical physics, the probability distribution ends up being exponential function of energy, okay? That is if you have time reversal symmetry, so you can cancel, and then you have detailed balance, and then you have this. In a nutshell, this can be summarized like this. Energy is additive, whereas probability is multiplicative, right? So that then solution of these two equations is exponential function, okay? Yeah. Since I saw this slide, maybe I save one word. So the rate of transitions from here to here is proportional to occupation number of the initial state, this and that, times the probability of transition. But there is also reverse transitions proportional to occupation numbers of final states times probability. If the laws of motion have time reversal symmetry, you cancel out those W's, and then you end up with equation for probabilities and solution of this exponential function. Of course, there are many other derivations in textbook, for example, by maximization of entropy. If you have a closed system and you have a fixed amount of, isolated system, there is fixed amount of energy, this energy is divided among atoms, and the way it is divided really by maximizing entropy. So if you maximize entropy subject to constraint, Lagrange multipliers and all that, and you end up with exponential distribution. So that's pretty much the summary of statistical physics, which I'm sure you all know. And now we move on. I often say that I made only two contributions in this field. One I will show you now, and second I will mention later. My one contribution is this. I replaced the label. So watch here. Now we're doing economics. Okay. So now we have an ensemble of economic agents, like people in this room, for example. Okay, and we engage in transactions. We consider monetary economics. Okay. So suppose I want to get a bottle of water, from Andy. So I give him $5, and he gives him a bottle of water. Okay, that is our collision, interaction. Then what I do, I drink water. Water disappears. I fly away. We never see each other again. But you see, his money balance is $5 up, and my money balance is $5 down, right?
That thing is probably not worth $5.
Yeah, I said 5 is just an arbitrary number. Yeah, I put an arbitrary number. Okay, but the point is, you see, there is transfer of money from one account to another account in economic transaction, right?
I mean, my joke, but I'm also just wondering, in principle, maybe the conservation law is sort of naively could be.
Yes. You see, as you can see in this transaction, there is local conservation law. I literally pulled $5 bill and gave it, or I did digital transaction. Because all these things, all transactions in these days, money is really digital. Money is really digits. Okay, so it's money. It's really numbers. It's a bits of information which are sitting in some computer's accounts, and they are governed by laws of accounting. Not laws of nature, but laws of accounting. What are laws of accounting? Laws of accounting, as you know, if anybody knows, financial office, you move digits from one account to another account, the other account, the other account. So we ordinary people like you and me, we are only permitted to get money and to give money. We're not permitted to create money out of nothing. So of course there is like central bank. Central bank, yes, because they have central authority, they can print money. So they act as a like external source. So in other words, we are ordinary agents of the economy. We only can move money around, okay? And then there could be external source like Federal Reserve, like central bank, who can inject money. But that's a different story. I mean that still doesn't violate conservation, because this is our system, and this is money crossing the boundaries, like energy comes from the sun, to us on Earth. That doesn't violate conservation law. It's just external injection of money. Okay. But what I'm saying is a local conservation law of money. There may be complications. I mean, banks and other things. Okay. But in terms of simple-minded. Keep in mind, these are all simple-minded ideas, which I was kind of driven 25 years ago. Simple-minded, an idea that money is transferred, right? Okay, because if somebody says no, I can make money, tell this to your chair, right? If you have budget problems, ask that guy who says I can create money out of nothing. Okay, any chair can tell you that it's not possible. Okay, any chair of the department, I think. Okay, fine. Anyway, so bottom line is this. It looks similar, like there is there's conserved quantity which is redistributed in transactions. And the question now is, what if you leave it for long enough time? Let's consider isolated. What will be the equilibrium distribution of money in that system? Okay, and basically I made a hypothesis. Since in physics is exponential, I made a conjecture that it will be also exponential in that system. Okay. There are caveats. For example, I mentioned time reversal symmetry, which may not apply, in which case it will not work. But at least in some class of systems which do have time reversal, then it should work. Okay, I will get to this maybe a little bit more later. But in any case, let me show a computer simulation to illustrate this point. Let me show a computer simulation. Unfortunately, I have to get out of this mode because it's an Apple problem. Okay, so. So anyway, it's a computer-based simulation where you have basically, now I have to use this pointer, unfortunately. We prepare the system, we give initially all agents the same amount of money. So we prepare a system in the state of perfect equality. Everybody in this room starts with exactly the same amount of money, let's say $10 or something, 10 units, whatever, okay? So distribution is delta function. So that's state of perfect equality. That's like initial condition, okay? And then I start running computer simulation. So I pick a pair of agents. Now, to keep it simple, in this simulation, every transaction is $1. Okay, it will be more complicated, but less. So I pick a pair of agents, transfer $1 in random direction. Another pair of agents, transfer $1, and so on. So every transaction is $1 for agents picked up randomly. Let's see what happens. Okay. Okay, so you see, I started running simulation, I stopped it, okay? Because you see this delta function distribution immediately broadens, okay? So this is like diffusion. It's kind of Gaussian shape like diffusion. It's diffusion in money space. So because of random transactions, some agents end up with higher money balance and some agents with lower money balance, okay? Keep in mind that the center of mass, the first moment, is constant because of conservation law, but the second moment, the width of the distribution is not constant, it increases, like in any diffusion. Like any diffusion, it increases the width of the distribution, right? So, but let me run it further. I stopped it. If I run it further, let's see what happens. It keeps spreading and spreading and spreading, and now you see it becomes asymmetric. Why it is asymmetric? Because, come on. Okay, because there is boundary condition. I didn't mention, but I put boundary condition at 0. That means in this simulation, I do not allow money balance to go below 0. Okay. So in other words, if I spend all money, if I still want to buy water, but I don't have money, I cannot do that. Okay. So technically, it works like if agent is supposed to pay but has no money, we skip transaction, go to next pair. Okay. So in this way, nobody can go below 0. So 0 money balance becomes like ground state. Like ground state in physics, the lowest possible energy, okay, by this. And so that makes a boundary here at the ground state. But there's no boundary on the other side. And so basically distribution becomes asymmetric because probability density accumulates near the boundary but can spread the other way. So now it's not Gaussian anymore, it's very asymmetric, okay? And so if you just keep running the simulation long enough, it eventually approaches to this red curve, which is a graph of exponential function. It approaches exponential distribution and then stays there. Okay, so exponential distribution represents equilibrium distribution, meaning transactions continue, money still move around, but overall distribution doesn't change anymore. That's a steady state, steady distribution. Okay, what is shown on the bottom graph, okay, this is entropy. Entropy is a function of time. You see, initial distribution, perfect equality, had 0 entropy. Because if you remember, entropy is logarithm of multiplicity, multiplicity number of combinatorial ways to prepare this distribution. So a perfect equality, there is only one way to prepare it. Everybody gets $10, that's it, only one microstate. Logarithm of 1 is 0, so initial state has 0 entropy, it means very low entropy. And then as the system evolves, entropy increases by second law. Entropy increases until it reaches maximum, okay, and then just stays there. Okay, so this exponential distribution, in other words, corresponds to maximum entropy. Okay, I'm sure you all know that. In fact, I use this simulation to teach statistical physics because it's easier to explain it with money. Okay, right? Okay, so and though from that perspective, I would consider. So there are several messages here. One message is the state of perfect equality is totally unstable. You can prepare it, maybe. You can try to prepare it, but the moment you start doing anything, it will spread out. It's totally unstable. On the other hand, this exponential distribution is stable because it corresponds to maximal entropy. So I, from physics point of view, I consider this like natural inequality. Natural meaning, you see, this originates just because of random processes. Okay, and in this simulation, by the way, there are no preferences. First of all, it's kind of like very stylized model of like free market, meaning any agent can transact with any other agent. There's no connection all to all. There's no structure. Anybody can interact with anybody. And also, all agents are treated equally in statistical sense. Everybody has the same probability to be picked up for any transaction. There's no preferences, biases, whatever, in statistical sense. But of course, as we know, in lottery, everybody has equal chance to win, but it doesn't mean that everybody actually wins. So the equality of opportunities doesn't mean equality of outcomes. Okay, and that's what we observe here. So what we observe is highly unequal distribution, which means there are few agents with high money balance, right? And many agents intersect with low money balance. Okay, so there are few rich agents and many poor agents, which kind of qualitative resembles the reality. So I'll answer the question. Go ahead. Mm-hmm.
So but this would mean that any
yes, correct. Correct. As long as you use the same rules, okay, it doesn't matter what were initial conditions. This is state of maximal entropy, and this is the attractor. So no matter what was the initial condition, it will come to this attractor. Okay, yeah. Okay, great. So that's pretty much gives summary of my first paper and gives the motivation, etc. And I thought I would just finish this and just, I get it off my mind, publish it, and move on with my usual condensed matter. But, being physicists and so on, what the question was, does it correspond to reality, meaning to any real data, etc.? It's just pure theoretical fantasy or what? So next slides will be about real data, okay? Any question about this part, briefly? Yes?
If the system allows for credit below but with a maximum credit,
yes. Okay, so question basically is credit is the same thing as debt. Okay, since the question was asked, I unskip this slide. Where is unskip? Unskip the slide. Okay, so this is answer to a question. Okay, so next step would be when I talk to this to economists, and they say, "Oh, this doesn't make any sense because you don't have credit. Everything else on credit. This is totally meaningless model." I said, "Okay, fine. Let's introduce credit, which is the same as debt. Credit and debt is exactly the same thing. Debt sounds like not a very good thing, right? Credit, it sounds great, but it's exactly the same thing. It's exactly the same thing." Okay, so remember the simulation I showed you. Remember, initially it was spreading, okay, but then it stabilized. Why? Because there was a boundary, okay? Suppose there was no boundary. So what is debt? Debt is, from physics point of view, is basically negative balance. So suppose I want to buy this, water, but my balance is 0. I still want to buy it. So what I do, I go to a bank and I try to get a loan. So let's say I get $100 loan in a bank. My balance was initially 0. Now I borrowed $100 from the bank, okay? And now what is my balance? So borrowing money, creating debt, is like particle anti-particle creation, right? Because what I get $100 cash in my hand, but I also have $100 debt, $100 obligation. So my net balance is still 0 because I had debt obligation at minus 100. It's like negative, my balance negative, positive. So my net balance is still 0. So by borrowing money does not violate conservation law. It just allows negative values of money effectively. So in other words, that is, to me, is like negative money. So my balance is still zero. I use this $100 cash to buy some water, so some of those money go to Andy. So now my cash balance is below $100, but my debt stays with me, right? So my net balance becomes negative, right? So now my balance is negative. So permitting debt, it means you allow negative balance. So it means there was a boundary, and now we allow, go on negative side. And now the question is, should there be some other boundary? Okay, let's start with extreme case. Suppose there is no boundary. That means you need to borrow. Need more money, borrow. Even more money, borrow, not a problem. Okay, no limit on that. That means the distribution will be spreading symmetrically. That means the debt will grow unlimitedly. But because center of mass, the first mode, is fixed, there will be increase of it will be growth of negative money, which is debt, and corresponding growth of positive money, because center of mass must stay the same, right? Okay, and it will never stabilize. If you don't put boundaries, debt does not stabilize by itself. Okay. So it will just grow unlimited. People debt go unlimitedly, and positive money grow also unlimitedly. And that answers another frequently asked questions: how to get rich? Okay, I mean super rich. Okay, so to get super rich, you have to put somebody else in debt, right? Otherwise, you run it again constraint. But no limit on debt doesn't sounds not right. I mean, there has to be some limit. Okay, let's introduce some limit. Let's say you can borrow, but up to a limit. Okay, so then let's say this was the initial boundary at 0. That was your initial distribution. And they say you can borrow, but up to maybe limit 800 units. Okay, so then run simulation again. And after we run simulation, but you cannot borrow more than 800 units. That's it. Okay, so what we run after run simulation, we get new exponential distribution with another boundary. So allowing people to borrow up to this limit simply shifts the boundary condition. Now you have a new boundary condition, and you have new exponential distribution. And effectively, by allowing people to borrow, you simply, it's the same as giving them that amount of money. Okay, so it's still exactly the same. And by the way, also some people ask about interest. Some people think that interest may stabilize debt, right? But you see what happens. If my balance is negative and interest is accumulating, my balance becomes even more negative, right? Whereas banks count my debt as asset. And because of interest, this asset becomes even bigger asset. So what interest does, it pushes these two opposite sides even more. So interest actually produces destabilizing effect. So the only way to stabilize is actually bankruptcy, when you say no more. And that may stop it, if you have guts to actually implement it. So anyway, so just allowing people to borrow up to limit, just shift the boundary. Okay. Another option is because I forget to say, you see this parameter temperature. It's exponential distribution. It has parameter temperature, which in physics is average energy per degree of freedom. In this case, it's average money balance average money per person. If you start with $10 per person and then convert it into exponential distribution, it will be exponential with parameter, I call it money temperature, which is $10. Because that money temperature parameter is just average money per person. Okay, and because you permitted people, you shifted boundary conditions. But you have to measure it relative to the boundary, because you shifted the boundary. Effectively, the amount of money per person became bigger, and that produced bigger temperature by the distribution. Absolutely. Okay. But another option is you may want to impose limit not on individual balances, which is not really the case, in reality, yeah? But on the total debt in the system. And this is done by something called required reserve ratio in economics. Maybe I'll skip the detail, but point is, if you want to impose constraint on total amount of debt in the system, then you have to again maximize. You have now two constraints. You have constraint on positive money and constraint on negative money. Then you maximize entropy, end up with double exponential distribution both ways. Okay, you have exponential distribution of positive money and of negative money. Nice, I like it, stable, stationary, double exponential, and the required reserve ratio. Basically, what required reserve ratio? I put money in a bank, okay, and I have put $100 in a bank. I think I still have it. But banks lend this money to somebody, like Andy borrows this $100, right? But no, bank are not permitted to lend all $100. They must keep a fraction on reserve. So they keep $10 on reserve, and only they permitted to lend $90. So Andy gets $90 loan. So he gets this money, does something. Eventually, this money gets deposited in some other bank. Some other bank has $90 deposited. Okay, of these, 10% will be taken out, and lend it to somebody else and somebody else. You basically have geometrical progression, which converges because you got smaller amount of money. At some point, all available credit will be exhausted. And amount is controlled by this fraction you put aside. And the inverse of it is called money multiplier, because the total amount of positive money will be increased by exactly the opposite. If it's 10%, it will be money will increase by factor of 10. So anyway, but it's written in every economics textbook and the graduate. The only problem is I talk to economists and say, oh, you know, it doesn't really work this way. Because they told me that, in fact, this required reserve ratio is inconsistently enforced. For example, in the US, only on retail banks, not on investment banks. Some countries don't even have required reserve ratio. Some people like China do use it. So basically say it's not really used as a tool of American financial policy. China does use it, but America does not. And I ask why the hell it is in your textbooks if it doesn't correspond to reality. Because it's easy to explain to the students. Yeah. So bottom line, required reserve ratio simply because it's implemented inconsistently. It does not produce actual constraint on debt. And if there is no constraint on debt, there is no stationary state, because debt does not limit by itself. There is no such thing as equilibrium debt. So bottom line, once you relax this boundary condition, you open Pandora box to all kind of instabilities. And in fact, one can argue that many of these economic crises are really crises of debt accumulation. Debt accumulates, and then we have crisis, subprime mortgage crisis, and you name it. It comes over and over because it's all about boundary condition. Okay, sorry, I exhausted quite a bit of my time. Let me move on to data, okay? Because that was all theoretical. This is computer simulations, But what is reality? Now, here is a story. It turned out that it's difficult to get data on money balances. It's just if I had a friend in a big bank, could have shared data with me, but in 25 years I didn't find any friends like that. Okay, but what I found is that there is a lot of data on income distribution. Okay, because people pay taxes, that is reported. There is also census. There is a lot of government, publicly available data on income distribution. Now, income is not the same as money. Meaning income more like flux of money, right? For example, annual income. That means money you get per year. So this is, like in physics analogy, it will be like energy per time, which is like power. Okay, so it's not exactly the same quantity, but whatever. There is empirical data. So let's move it to the second part of the talk, or maybe short by now. Let's just use an empirical data on income distribution because it is available, widely available. Okay, that's what we did in the second paper in 2001. So we download the data from Census Bureau, and the beauty is because you download raw data. It's sample data. They sample maybe it's a fraction, a sample of population. It's not all population. It's only sample. But anyway, you download raw data, make a histogram. So basically, this is annual income in thousands of dollars. In this case, up to $120,000. We divide it into bins and count how many people have income, in these bins, and make a histogram. Okay, so this is individual income. Okay, and what this is a histogram. Okay, the data, and this is fit to exponential function. And you see, it's pretty good fit. I mean, there is some deviation at the low end, but keep in mind, this is below $5,000 per year, which is a very, very low income. So, you may see some deviation near the boundary, but overall, it's pretty good exponential. But of course, as we know in physics, to really confirm it, to really confirm exponential, what you should do, use log linear scale. You take logarithm of this probability distribution, plot probability density, plot it in logarithmic scale versus income, and then data point fall in a straight line. Okay, so this is the same data, just plotted in log linear scale, fall in a straight line. And this deviation, by the way, doesn't look so big in logarithmic scale because that's appropriate scale. And I can tell you, I have been doing also condensed matter physics. And by standards of condensed matter physics, this is an excellent agreement. In condensed matter physics, I see much worse things. People say, "Oh, that proves my theory." Okay, so by far, maybe not high energy. It's not maybe not the Higgs particle, not high energy standards maybe. And I cannot tell you how many sigmas. But by standards of condensed matter physics don't ever use sigma. They just look at visual figure, and that's good enough. Okay. So anyway, we published second paper titled Evidence for Exponential Distribution of Income in the United States. Okay, and economists has no idea, but they still have no idea that it is actually exponentially distributed. This empirical fact. Okay, fine. So far, so good. But this is truncated at certain income. Okay. And okay, so maybe I'll tell you the story. We submitted first paper to PRL. Of course, it was rejected. Eventually, it was published in some European journal. But the referee said, Well, it was kind of argument. Said, well, since the days of Pareto, remember Pareto, the second portrait. Since Pareto, we know all those distributions are power law. And you're proposing some stupid exponential law. It makes no sense, get rid. And there was no, like everybody knows it's power law. And there were no references, no nothing. I mean, like, okay, what? I said, okay, the argument of the referee in physics in FRL was actually empirical. The argument was not theoretical, that the theory does make sense. It said it just agree with the data. So we look at the data, it does agree with exponential. But where's power law? Which everybody knows. So it turns out there is power law, but it's in the upper tail. So you see, census data is truncated at this income because it's a sample of population, etc. So we went then to next a different source of data, to IRS, internal revenue source. We get to tax data. And in principle, everybody is supposed to pay taxes, file tax returns. So sorry, not the same thing, file tax returns. Okay. And so we have 100 million, data tax returns every year. Okay. And so IRS actually publishes this data, meaning not individual data, but aggregated data. They have a statistics of income research division that aggregate the data and publish. So this data, blue data points, are taken from this IRS publication. And those extend to much wider range. Okay. So anyway, so the inset, this is called adjusted gross income. So this is
that data actually just stop at 1 million?
Yes, because it was for 97, but I'll show you next slide. I'll show much further. Next slide. Yeah, next slide. This one, I'm showing this.
Even in 1997.
Yeah, because we did this around 2000, and that was the latest available at that time. But next slide I'll show you for 36 years, up to present, recent time. Okay, next slide, yeah. But bottom line, what point is, this is log linear scale. This is basically cumulative probability distribution. That's integral of probability density. So the good news: integral of exponential is exponential. Integral of power law is power law. So we can use this cumulative integrated probability, integral of probability densities. So that's why it goes to 100% because it's an integral of probability density. So anyway, long story short, the inset is in log linear scale. So this is called adjusted gross income, meaning income, definition of income according to IRS, but I'm lying in your tax return, whatever. So it's log linear, and you see data fall in a straight line, beautiful straight line, up to 100K income. This is 97, very long time ago. Log scale. And this is totally different source of data, and it's still exponential, okay? But the main scale is log scale. So now income is in logarithmic scale, both probability logarithmic. This goes up to $1 million per year, that's income, okay? And what you see, the lower part, the upper part becomes straight line in log coordinates. That means power law. And the lower part, that is that exponential fit of the data. So basically what you see is, again, data-wise, evidence for two-class society. And when I say two classes, this is like data scientist definition. You get data points, you fit with the simplest mathematical functions, exponential here, power law here, and you hear two-part, composition of the distribution, right? Okay, that's what. But of course, maybe that you didn't mention. I was educated in Soviet Union. Okay, so Karl Marx Capital was mandatory reading. So I surely heard about two social classes before. Okay, and now many years later, I just look at the data. Here's in your face. Here's your two classes. In the data. Obviously, in Capital, Karl Marx, you will never see this kind of graph. You'll see lots of discussion of two classes and class struggle and all that. Words and millions of words, and no single data graph. But that's what it is. Okay, that's because like an appendix to whatever. Okay, now that you have this decomposition, okay, we can then take intersection point defined as an empirical boundary between the two classes. And there are only two classes. There's upper class, power law, and there is lower class, exponential. Okay, and by the way, there is no such thing as middle class. I mean, it's not in the data. It's not in the data. And by the way, as I learned in literature, in economic whatever, there is actually no commonly accepted definition of middle class. So whoever writes newspaper article of like disappearance of middle class, whatever, you name it, everybody who writes article makes up their own definition of middle class. Okay, because there is no commonly accepted definition. So there are only two classes. There is upper class and the lower class. Okay, and then we can say, look, how many people are in the upper class? Okay, so we take this intersection point, this upper class, right? So go here, this is cumulative, this is 1, 2, 3%, so about 3%. So upper class is about 3% of population. Number may change, it may be 5%, it will change over time, but still, few percent. Okay, and the rest, I pretty much assume all people in this audience in the lower class. Okay, well, not on this graph, but the next graph, you can put your income and check which class you belong, this or that. Yeah. Yeah, I mean, you can go to my paper and check, yeah. There may be a few exceptions. In my department, there may be some, maybe one person who is exception, maybe one, but no more. Okay, maybe two. Okay, I'm certainly here, by all means. Okay, so, and this is, if you probably heard about the 1%, okay, this is the 1%. It's not 1%, 3%, but whatever. The point is actually correct. Okay, so, yeah, so this is a two-class distribution. And by the way, this are actually known also in physics. Once I was, searching for literature, etc. For example, we have the Goddard Space, Center in Maryland. Okay, sends satellites and measures, solar wind and cosmic rays and all that. And in all this literature, I'm not astrophysics, specialist, but what I gather, this kind of distribution is very common there. The lowest part is exponential, called thermal, and the upper part is powerful, called superthermal. Okay, so this kind of distributions exist in other places as well. Okay, great. So now, what's next? What's next? Yes, Andy's question. Okay, so this was one particular year. And then over time, we're doing more and more. This was 1 year. Now, since then, we're doing more and more years. Okay, and so this is now from the latest paper. And this is 36 years of data from 83 to 2018. Okay, so because now we compare different years. Okay, so lower part is exponentially distributed. It has a parameter which I call income temperature. So, exponential distribution has a scale, right? And we call it, and it is determined by slope. In the log linear graph, the slope of the straight line determines that income temperature. So for each year, which is basically the average income of the exponential part of the distribution. Okay, and so for every year from 83 to whatever for every year we make this log linear graph. It is a straight line. From the slope, we extract income temperature. And then importantly, we normalize income to income temperature of this year. So this is normalized income. Income normalized to income temperature in this year. Once you do this normalization, then data points collapse on the same line. So specifically, the lower part is exponential. It means a straight line log linear coordinates. So if you use this coordinate being, normalized income, that means by construction, make slopes all the same. Okay, and you see these data points collapse for many years on the same straight line. It's just separated visually for these years, and for this year, they're simply shifted for clarity. You may also notice that the range of straight line actually decreases. It's extended up to 5 times the average income in a long time ago. Now the boundary is more like 3 times, because you may ask, where is the boundary between the lower and upper crossover point? So now it is more like factor of 3. If your income is above 3 times the average income, then you are in the upper class. It used to be a factor of 5. Now it's factor of 3. So anyway, so the lower part is no. This is United States. Okay, this is United States, and these are nominal dollars. There are no adjustment for inflation, etc. Because people file tax returns every year, and those are reported in those years. And then you go to the library and collect all these. So all of these are initially reported. It's just dollars. It's just dollar amounts. But the average income increases. In fact, during this time, the average income increased by factor 2.5 in nominal dollars. You see, and this is pretty much inflation. We have another graph which you compare it with consumer price index. Conserved. Yes. Okay, fine. I guess your question is this: if money is really conserved, how we can possibly have inflation? Right? I mean, it couldn't be. Well, because reality is that there is injection of money into the system. And how it happens? Well, short answer, maybe not full answer, but short answer. Government debt. Because as you know, the debt of US government keeps increasing, right? And I told you the story. To increase positive side, you have to increase negative side. Okay? So US government essentially effectively, there are some caveats, but effectively prints money and inject them in the system. Together with central bank, etc. But bottom line is there is injection of money from the central authorities in the system, and that increases money balance. Okay, and so that increases income. But if you normalize for this income temperature, which is basically average income, if you normalize to average income, it's a universal curve. Yeah, so in other words, relative inequality, this is log linear scale. Again, this is just separated for different years, but it's the same thing. So bottom line message here is the following. In 36 years at least, okay, relative inequality, okay, within lower class doesn't change at all. It just stays exponential, okay? And my physicist reason for this is because it's maximal entropy, right? So most of the population is like thermal bath. It's like a thermal equilibrium, and it just stays exponential. Maximal entropy simply doesn't change. Scale of income renormalizes, but if you normalize to it, there's no change. See, data points collapse on the same curve. On the other hand, the upper tail, it has dynamics, has significant dynamics. We see those straight lines for parallel tail, they do not collapse on the same. So there is significant dynamics in the upper, and I'll show you this on the next slide in more detail. Okay, fine. Okay. So once we get this decomposition, so what is the advantage? This kind of thing, it allows you to describe the whole income distribution with only a small number of parameters. In fact, 3 parameters. You only need 3 parameters to fit the whole distribution. 3 parameters is temperature for the exponential part, the Pareto exponent for the power law, and the crossover point. And these 3 parameters captures basically very much all distribution, okay? So this is like, roughly speaking, like, Kepler said that gigabytes of data on positions of planets, right, can be compressed in a few parameters for ellipses. They're just ellipses, okay? And all you need to know a few parameters of ellipses. You don't need to know every single point. You can reconstruct them from that, okay? So now once you reduce everything to a small number of parameters, then you can study time evolution of those parameters. That will be next slide. Okay, so this is a busy graph. I will maybe not go through all of it because I want to get to the last point about global inequality. But anyways, this is time scale from 83 to whatever it was, 2015 or so, yes. Okay, so let me start with the upper panel quickly. Important question is the following. Interesting question is, what is the fraction of income that goes to the upper class? Remember, the fraction of people in the upper class is about 3% or so. Actually, this is a graph. This is tail population. Its scale is here. Okay, so because you can decompose now everything. So the number of people in the upper class actually have been increasing. The percentage of people in the upper class have been increasing from about 1% to, well, maybe 3, 4, 5% or so. Not huge, still below 5%, but nevertheless some increase. So the tail actually has been expanding to some degree in terms of number of people. But you may ask, what is the amount of income? What fraction of income goes to the upper class, right? And it turns out there is a simple formula one can derive. You can take average income, meaning of everybody, all L people, the mean income, and take a difference with the temperature, income temperature. Remember, temperature is the average income of the lower class. And this is average income on the whole ensemble. So the difference is what goes to the upper class. It's a simple formula can easily derive. And this is the graph, red curve. And scale is here on the left side. So from, say, 85 to like 95, it was roughly speaking about 10% of income was going to the upper class. But then it started to increase rapidly, up to almost 20% from 95 to 2000. Okay, so what happened? What happened from 95 to 2000? Some people may be young, old enough like me, I get my faculty position 93 at Maryland. Okay, anyways, dot-com bubble. There was a bubble in the stock market. Okay, so during this bubble, everything was growing. Average income, temperature is income of the upper class was growing, but the income share of the upper class was growing much faster. And keep in mind, this is income reported to IRS. This is not just stock market. This is actual cash flow that you get. I mean, not you, but people who handle your, your retirement accounts at Wall Street. Okay, so but that was a bubble, and this bubble crashed. Okay, so it crashed, and the income of the upper class shrunk. I know, I remember those times. I lived through those times. Some of you also did. Okay, and then next bubble started, real estate market. And I remember people saying, oh yeah, stock market is so risky, so bad, but real estate, prices of houses never go down. Yeah, and so that was next bubble. Put your money into real estate, then upper class income, share of the upper class, share. Increase, again, exceeded 20%. But that was a bubble, so it crashed, And that was big financial crashes. And then what? You see another peak. What is that? I call it quantitative easing bubble. So what's quantitative easing? That's injection of money by Federal Reserve. Okay? So because when the whole thing crashed, all these bankers, etc., came to Feds and said, bail us out or worse. In other words, if you don't bail us out, banks, financial system, we'll take down the whole damn economy down. Okay, and so yeah, sure. And so the Federal Reserve quadrupled their balance sheet. They used to be below $1 trillion, now it's like $4 trillion. Okay, so they quadrupled $1 trillion because they can, because Federal Reserve can. Okay, and so they created money out of nothing. But there is a catch. The catch is Federal Reserve is a bank, Federal Reserve Bank, right? It can only deal with banks. It cannot give NSF grants to you and me. This is government branch, right? They can only give money to banks or financial institutions. And that's what they did. They printed money out of nothing, gave it to financial institutions. They say, great, thank you very much, give us even more. Okay, that produced another peak, another raise of share of the upper class. Okay, so long story short, conclusion, I have to wrap it up and go to the last part of the talk. Bottom line, income inequality peaks during speculative bubbles in financial market. Okay, that's what you see here. But on the other hand, if you look at this, it looks like this is like on average, it's kind of flat. It's like bumpy plateau. It's bumps, yeah, but it's kind of overall plateau. So in fact, what you see, this is all Gini coefficient. I mean, I'm not sure I will get time to get to Gini. But anyway, Gini coefficient is a measure of inequality. I will explain it in the next slide. It has been increasing, and then it has these bumps, and basically, but overall plateau. And there's a formula. Well, it's a theoretical formula I derived relating Gini. Gini is what all economists use. And this is a fraction of income going to upper class. The message here is the following. See the agreements between the blue data points and the blue curve? This agreement, basically, the message is this. All dynamics of inequality, income inequality, starting from the United States, can be completely described by decomposition of income between upper and lower class. So it's really the fraction of income between upper and lower class that determines overall income inequality as measured by Gini coefficient. Okay, yeah. And also last thing about here is Pareto exponent. This is Pareto exponent. And scale is here. Pareto exponent used to be close to 2, and then it has been decreasing at least up to 2000. Okay, and decrease of Pareto exponent, that means the tail is getting fatter. It's getting fatter tail. And around 2000, I remember I was in Princeton, and there was Boris Altshuler there and Lerner, my friends from colleagues from Soviet Union. I showed them early version of the graph. Remember, this was not available at that time. And they said, oh, I mean, if you extrapolate this, by now it should reach 1. Pareto exponent should have reached 1 if you just extrapolate. 1 means what? Its tail becomes unnormalizable. That means total income going to the upper tail would integral would diverge. That means the upper class would take everything. And they say, ooh, revolution is coming. And they said my Soviet colleagues. Yes, but what happened is it actually stabilized. After 2000, see, it doesn't change anymore. It basically got around 1.5. So this revolution was prevented, and at least for now, I'm not sure. This year I don't know, but so far. So in other words, the biggest growth of inequality was actually up to 2000 or so. After 2000, it's more like bumpy plateau with crashes and bubbles and crashes. But on average, nevertheless, it stayed more or less constant. Okay, so I'm running out of time. And what I want to get really to the last part of the talk, and this is about global inequality, okay? Global inequality. I have to show you briefly one slide. This is about Lorenz curve because that's needed for the second part. Very quickly. Lorenz curve, this is what economists use all the time. The problem is, when I make this graph, my income scale can go all the way to infinity. Income can be many $1 million, right? I have to truncate it somewhere. But there is a way to show the whole thing in a limited amount of space. And basically it works like this. It's a parametric graph. You pick some income R, and you define horizontal coordinate x and vertical coordinate y. Okay? So x is basically integral of probability density from 0 to r. So that's essentially a fraction of population with income below r. So you pick some arbitrary income r, and this is fraction of people whose income is below r. Okay, it's cumulative function. What is vertical coordinate? You take income and integrate with this function and normalize it. So this is the cumulative income of all those people whose income is below r. Okay? So in other words, this is cumulative population here, and this cumulative income. And then you run this parameter r from 0 to infinity. And then you get a curve that starts from 0, 0, ends up at 100%, 100%. So by definition goes like this. That is definition of Lorenz curve. Lorenz was an economist in the early 1900s. Okay, but here's the deal. So suppose my distribution is exponential. If it is exponential, I can plug it here and do integrals analytically. I just calculate the integrals analytically, and I eliminate R and calculate the Lorenz curve. This is the formula for the Lorenz curve for exponential distribution. You see this universal formula, there are no adjustable parameters because everything is normalized, okay? It's dimensionless. And this is shown by the red line. So the red line is the Lorenz curve for exponential distribution. And the data points are distribution in 1983. In 1983, overall in the United States, the income distribution was pretty close to exponential in 83. Then what happened by year 2000? It shifted down. The blue points, it shifted down. Why? Because of growth of the upper tail. What is upper tail? The upper tail, you have a small fraction of population which accounts for significant fraction of income. For example, in this year, 2000, maybe a couple percent of upper class accounted for 20% of income, okay? Okay, so this is income of the upper class, which is significant income, but very small people. And this is the, So effectively, the amount of income available to lower class now is decreased by 20%. So all you have to do, take this curve and scale it down. You have to compress it vertically, okay? Because income to the lower class is smaller. You multiply by factor 1 minus f. And f is a fraction of income going to the upper class. And if you rescale it vertically, you have a very good agreement. So it shows this is exponential distribution, and this jump is the upper class, okay. And Gini coefficient for the exponential happened, so what's the definition of Gini? Gini coefficient is just another measure, it's the area. Okay, so suppose if everybody had the same income, it would be straight diagonal line, because income would be proportional to population. So straight diagonal line corresponds to perfect equality. Maximal inequality would be a line like this. So everybody has 0 and one person has everything. That's maximal inequality, okay? So you can take measure of inequality is the area. You take area between the diagonal perfect equality and the actual Lorenz curve. Take this area and normalize to area of the triangle. So that's the definition. Now it turns out, because I know this Lorenz curve analytically for exponential, I calculate Gini. It happens to be 1/2, 50%. So Gini coefficient is bound between 0 perfect equality and 1 maximal inequality. And for exponential, it's exactly in between. So that's corresponds to exponential. Okay, and then if you have tail, you shift it down, Gini increases, becomes 1 plus f, where f is the shift, the fraction of income going to the upper class, and that formula actually agrees very well with the data I showed you before. Finally, I'm done with income inequality, and now I want to discuss global inequality, okay? Because, you know, there are rich countries and poor countries in the world and all that. How about global inequality? And so, sorry, this part I have to skip because, yeah, this is some mathematical Fokker-Planck equation, you know, but that will be too mathematical and there's no time, so I skip it. For those who want to hear more about mathematics, I can do it separately. But anyway, so how to measure global inequality? Measuring by dollars would be tricky because you'll have like PPP, purchasing power, which is kind of complicated, you know, because different countries use different currencies. So you have to put them to the common denominator, exchange rates are, you know, problematic and all that. So we decided to look at energy consumption because, you know, kilowatt is kilowatt everywhere. So we decided to look at inequality as measured by energy consumption per capita, okay? And just to start, this is some just, okay, so this is energy consumption. Annual, this is annual consumption, you know, that means per year. That means you can measure it in watts, you know, energy per time is watt. Okay, so this is, you know, United States consumption as a fraction of total, which is pretty significant. In this year, what is this year? It is, they say, oh, it is 2010. Okay, China is also significant. India is much smaller. But look at the populations. US population is pretty small in relative sense. China is, well, about the same. India is big. So as you can see, if you do energy consumption per capita, it will be vastly different. It will be very high in US, middle range in China, relatively low in India. This is just an example of 3 countries, but there are many other countries. And now I show you all the data. So we get data. This is energy information, United States Energy Information Agency. And there are data. Data is available. We downloaded data. And so what we did basically is the following. We rank countries according to, so we have energy consumption per country, 200-something countries, and also population of countries. So we divide one by the other, we get average energy consumption per capita for each country, and then we rank countries by energy consumption per capita. So somewhere at the top is United Arab Emirates, but this is like outlier because population is very small, you know. So, but more typical, United States about 10 kilowatt. 10 kilowatt. Okay, the world average is 2.5 kilowatt. This is 2010. 2.5 kilowatts is like, you know, 2.5 microwave ovens. plugged continuously for everybody on Earth. Okay, that's the average energy consumption. United States, 4 times greater than global average. Europe, about 5, okay, half of American. China is right in the middle. Okay, India is significantly lower and so on. So anyway, as you see, there is big inequality in energy consumption per capita. And so what we do, we put this ranking plot, and ranking plot is actually the same as cumulative distribution. So this is effectively the cumulative probability distribution. And what we do, and given the previous thing, we plotted this is in linear scale. It means that this is in log linear scale. Take logarithm of this fraction of population as function of energy consumption, and they more or less fall on a straight line. So what you see, the global energy consumption per person is approximately exponential. So I showed you data showing income distribution is exponential. Now this is energy consumption globally is approximately exponential. And why is that? Because it comes from the same kind of philosophy. You have a limited resource. Energy primarily comes from fossil fuels. That's the reality of present day, most of it. Okay, and then you extract these fossil fuels, and then these fossil fuels are divided among population for consumption, right? In theory, they could have been divided equally. Everybody gets equal share of fossil fuels, right? But that's not how it works. That's not how it is divided. It is divided by maximization of entropy. You have a certain amount of fuels extracted. They divide among 8 billion people. In which way? By maximizing entropy. And that produces exponential distribution. That's, again, my hand-waving theory, physics explanation. But very importantly, it was not always like this. This is 2010. And now let me show you evolution over time. So this is Lorenz curve, I explained to you before, for global energy consumption, okay? This is for 1980, and show you evolution in the next few years. So again, to remind you how this is constructed again. First, we rank countries by their energy consumption per capita. This is 40 years ago, 45 years ago. United States, somewhere in the top in terms of energy consumption per capita. India is somewhere at the bottom, energy consumption per capita. And the way we construct the curve is the following. We start from 0, go to next country, let's say India, for example. This is population, so fraction of population. India has pretty big population, vertical coordinate, vertical displacement, and relatively low energy consumption. Okay, you get point here. Then you go to next country, say China, in 1980. Population is relatively big, but energy consumption is relatively small. We add population of China, and we add energy consumption per, and then we continue until we get to the top. So that's how the curve is constructed. Now, as you can see, there is really high inequality. First of all, you can divide it into 2 groups of countries. You see, there's like a kink here, like a cusp. There is group of countries with low slope and high slope. Now, by construction, the slope of Lorenz curve is energy consumption per capita. In other words, these are so-called developed countries with high energy consumption per capita, and this is so-called developing countries with low energy consumption per capita. And this is kind of the boundary, roughly speaking. That was 45 years ago. And Gini coefficient, remember the measure of inequality, is pretty high, 66%. It's really far from diagonal. High inequality in 2 groups of countries. Now let's see what happened afterwards. Unfortunately, I have to do this again. Let me show you computer animation, what happened to this. Oh, actually, I'm sorry. Actually, I don't have to do this. Now, I don't need to stop it. Sorry, I forget it. Okay, I don't have to do it. So now I'm showing you a computer animation. Well, okay, so what we do now, okay, so I'm running a simulation. So you see, the curve moves up. So as time goes on, okay, let me do it again. Wait a sec. Let me do it again. So let me. This is 1980. This is 1980. Yeah. Okay. Oh, it's moving, right? Okay. So as time goes on, the Lorenz curve moves up. Okay. Animation is a problem. Anyway, so points you see it moves up. Moves up, that means Gini coefficient is decreasing. That means global inequality has been actually decreasing. Okay. So in the last, whatever, 30 or 40 years. It moves up, and energy inequality becomes more equal in a sense that it moves up. And now the red curve for 2010, first of all, the kink disappeared. It used to be kink here, and now it's a smoother curve. It's a smoother. There's no well-defined boundary between so-called developed and developing countries. More like a smooth distribution. Why is that? Because China moved to the middle. Okay, you see, China is right in the middle, and the distribution is smooth. And it's pretty close. What is the black curve? The black curve is theoretical curve for exponential distribution. Here's my interpretation. My interpretation is the curve is moving toward the exponential curve, which corresponds to maximal entropy. So this is dynamics driven by entropy maximization. And it is accelerated by globalization. Because what globalization does, it better mixes the world, right? And brings it closer to a state of maximal entropy, okay? But once you reach this black curve, this maximal entropy, it stops there. So in other words, black curve is a tractor. If you started with low inequality, as was in simulation at the beginning of the talk, you start with perfect equality. Inequality increases until it reaches maximal entropy, this one. So it goes down. But if you start with very high inequality, this also has low entropy. And actually, inequality decreases until it reaches this. So anyway, we made prediction that once this curve approaches this black line, further decrease of inequality will stop. It has been decreasing, but it will stop about now, about 2010 or so. Okay. So this was prediction, but now this was the graph for energy, in the kilowatt per capita. We did the same thing for CO2, emissions. Okay, again, CO2 emissions by country per capita, the curve looks like pretty similar, very similar. There are some small variations. France has nuclear energy, but anyway, the point is that you see, inequality on CO2 emissions has very similar dynamics, very similar curves. France has a lot of nuclear power, so it's there. But overall, it's still pretty close to exponential. By 2000, pretty close to exponential. So we made predictions, will not change anymore. We just stay there. And finally, I'm coming to punchline. This is a punchline. I have a couple of minutes left. In fact, it is only 5 o'clock, but let me deal with the punchline. Gini coefficient for CO2, this is for CO2 emissions per capita. Gini coefficient has been decreasing. And we published first paper. Let me just show this. We published first paper in 2014, where data was available up to 2010. This is the black point that was available. In the last 10 years, it has been decreasing linearly. There was no sign of saturation. And we predicted that soon, once it reaches level of 50%, it will saturate and stop decreasing. So at the time we published the paper, there was no evidence for this saturation, okay? We published it. And then time passed, and in 2020 we published the next paper when data was available up to 2017. You see? And this is red data points. And red data points show saturation. So saturation, exactly the level predicted, 50%, which corresponds to maximal entropy. Okay? So this is a rare case when a quantum physics made prediction in the future, about the future. Yogi Berra, predictions are difficult, especially about the future. Right? That is the story. And that's what we did a prediction, and it got confirmed. Okay? And what was the basis of maximal entropy? And there was also some story. This is data from energy, information, energy. I have to tell this anecdote. And it happened to be that in College Park there was a workshop. There's an international workshop on energy, global research, It happened to be 1 year in College Park. I went there. And there were speakers, and was invited speaker from United States Energy Information Agency. And he's the chief energy modeler. He was given, of course, invited talk and all that. Can you talk?